In lesson 10, we start our discussion of electric fields. And before you go over this lesson, I strongly recommend you go to YouTube, go onto YouTube and watch this video here. This electric fields crash course physics number 26. So watch that video before you pause right here, watch that video, and then come back. I think it will definitely increase your understanding and your appreciation for electric fields. And here they are. You've now watched the crash course, um, and we're going to go over the notes. Just like force due to gravity, the force due to electric charges can act over great distances. So we're going to make a lot of comparisons in the study of electric fields with gravitational fields. Why? Because they're very similar, and they're different in some respects. Electric fields can be repulsional or attractional, whereas gravitational fields are only attractional. They only attract. So that's the major difference. Okay, without going into reading your notes, because you can do that, important concept right here. Electric fields are action at a distance. Same with gravitational fields. Then we talked about Michael Faraday, which we'll talk more about Michael Faraday later in the course, but he's the British scientist that came up with the idea of a field. And here's a basic definition. A field is sometimes defined as a sphere of influence. An object within the field will be affected by it. Okay, and then there's some more detail you can read there. And then we're going to talk about two kinds of fields. We have scalar fields that have magnitude but no direction. And great example there. Heat field from a fire. You can stand by and measure the campfire. You can measure the magnitude of the field with a thermometer. If you are close to the fire, you will measure a strong field. But if you move away from the field, the strength decreases, but you would not be saying anything about the direction, like 25 degrees Celsius south. And then we have vector fields, which are electric fields and gravitational fields are both vector fields, and they have magnitude and direction. Electric fields are vector fields that exist around any charge, positive or negative. So anything that has a charge other than being neutral, which I guess technically is a charge in itself, is going to create a field around it, just in the same way that anything has mass creates a gravitational field around it. Anything that has charge creates an electric field around it. If one charge is placed near the second charge, the two fields will touch and exert a force on each other. Note, the field is not a force, but it does exert a force. So what's that saying? It's saying basically if I have just a single electron here, it's going to create a field. The field is going to look like this, and you'll discover why eventually, why it looks like this. And there's an infinite amount of lines going in towards the electron. And then if I put a proton over here, a proton, those two particles are going to exert a force on one another, whereas the proton is going to be drawn towards the electron, or vice versa. But you can see that the field lines for that electron are all going into the electron, but the force line, the force vector for the electron is going in the opposite direction. Okay, which we'll again discuss in more detail. So don't mistake forces and fields. Moving on. Okay, how can we detect and measure the electric field around a charge? The easiest way is to place another charge, a known charge, in there and see how it reacts. We do need to be careful, since both the charges have their own field and will interact with each other, so that would affect the results. So we come up with this mathematical construction called a test charge. And it says physicists have defined something called a test charge as a mathematically perfect charge that can be brought near another charge, the source charge, to measure the source charge's electric field. The test charge is an infinitely small positive charge. That's very important. It's positive. It is a mathematical creation, so they don't really exist. So he says it's infinitely small so that its field will be infinitely small and will not interact with the other field, thereby changing the conditions or changing the measurements. It's sort of similar to Heisenberg's uncertainty principle. The more accurately you can measure the position of something, the more inaccurate your measure of its velocity is, and vice versa. Okay, since it's infinitely small, yes, blah, 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 we just discussed that. Now, again, we will reiterate that the test charge is always positive, and that way you can determine what the direction of the electric field is. So, for example, if I have some kind of unknown charge right here, that's a question mark, funny looking question mark. If I have an unknown charge here and then I put the test charge right here, we'll just call it T for test charge, and the test charge goes, and I let go of the test charge and it goes this way, I know that whatever this charge is in here, it must be positive because it was repelled by the positive test charge. If the test charge goes this way, then I know that the source charge would be negative. Example number 3, you have a steel ball, has an unknown charge on it. This is your source charge. You're trying to measure what the charge of the source charge is. When you place a test charge to the right of the source charge, you see the test charge move away to the right, determine if the steel ball is positive or negative. Okay, so here's my steel ball. We'll just call it SB for steel ball. You place a test charge to the right of the source charge, and from now on, I'm just going to put my test charges as a positive, because since they're positively charged, that doesn't mean it's a proton, it just means it's positively charged, and it is infinitely small. You place a test charge to the right, so I put a test charge here to the right of it, and you see the test charge move away to the right. Move away to the right. Determine if the steel ball is positive or negative. Well, if it was repelled by it, then it must be positive. Okay. Then there's these PhET demonstrations, which, yeah, you should play around with them. There's a lot of good PhET demonstrations of simulations regarding electric fields. Okay, now, measuring electric fields. And here's the way that I'd like you to understand it. I would like to go back to gravitational fields. Back to gravitational fields. So how do we measure gravitational fields? Well, we know this formula from Physics 20. And on your formula sheet, that's the formula that we kind of gravitate towards. Oh, no pun intended. Fg, the force of gravity, equals mg, just because we use it so much. But on your formula sheet, it appears as this: G equals Fg over m, right? And if you recall from Physics 20, that is measuring the gravitational field strength or acceleration due to gravity caused by any given mass. Right? And how does this relate to electricity? Well, first, let's just discuss this. So G is the gravitational field strength, and it's measured in newtons per kilogram or meters per second squared. Fg is the force of gravity the force acting on that mass, and m is obviously the mass. How does that compare to electric fields? Well, let's replace this with an E. So now we have an electric force, and then ask ourselves, we'll just do it over here. Now we have Fe. An electric field is not created by a mass. Well, yeah, technically it is, but the actual characteristics of an electric field are created by its charge. So instead of mass, gravitational fields are caused by any object that has mass. Electric fields are caused by any object that has charge. So we'll replace the m with q, and then we will change this. This is the gravitational field strength. We will use this symbol right here, E, with a line over it, and that will be the electric field strength. So there is a new formula. It's on your formula sheet. Once again, once we get into this kind of stuff, you will often use this form of it. Fe the electrostatic force on something equals the electric field strength times the charge, in the same way that the gravitational force acting on something equals the mass times the gravitational field strength. Okay, so hopefully that that tells you where this formula comes from, and here it is right here on your formula sheet. And the important things to know here are the Q here is the test charge. Okay, and then there's a warning there you can read. We have an example. The example is pretty straightforward. It says I place a 3.7 Coulomb test charge. Oh, that's a lot of charge. 2.7 meters to the right of a negative 7.94 Coulomb source charge. If there is an attractive force of 2.5 newtons acting on the test charge, determine the field strength of the source charge at that location. Okay, so you have to be careful on this example because obviously we're going to use this formula here that we just learned. The electric field strength equals the electric force acting on the object divided by Q. And what is Q in this formula? It is the test charge. So you can use that one, not the negative 7.94. You're going to divide those and you get 0.66. And what are the units for electric field strength? Well, force is always measured in newtons. Charge is always measured in coulombs. So the units for electric field strength are newtons per coulomb, which is not surprising given that the units for gravitational field strength, what did we just say they were? Newtons per kilogram, because gravitational fields are caused by masses. Electric fields are caused by charges. So that's not surprising. Very nice symmetry here in the physics world, which we see often. Okie dokie, and then you go down to your super important notes, which kind of goes over what I was just discussing. It compares gravitational fields and electric fields. So you can read that little tidbit. And then, having it for time, we're going to stop. This is going to be part 1 of the lesson, and then we'll do part 2 just so you because you've already watched that crash course video, so it's already been a long lesson. So part 2 coming right up.